Alrighty, welcome back. Let's try this again, shall we? So, we balanced the equation in the previous video, but just to quickly refresh, so I've got iron 3 chloride, which is reacting with hydrogen sulfide to produce iron sulfide and hydrochloric acid. So we've gone ahead and we've written the balanced chemical equation. So we've got 2 of the iron chlorides, 3 of the hydrogen sulfides, 1 of the iron sulfides, and 6 of the hydrogen chlorides. So now what we're going to go ahead and do is we're going to determine the limiting reactant. So what we're going to do is we're going to write the number of moles of each of these compounds. So I'm just going to grab a pen and I'm just going to write at the top here. So I've got FeCl3. And what information do I know about that? I've got 90 grams of it, so I know that. The other thing that I know is the molar mass. I'm just going to quickly go to my periodic table. So iron is 55.85 and chlorine, and I've got 3 of the chlorines, and that's going to be 35.45. All right, so in total, my molar mass of that compound is going to be 162.2 grams per mole. Oh, my screen is doing funny things. Apologies. Sorry, guys. Okay, so let's try that again, shall we? So then the number of moles, and I've just already rearranged my equation, is going to be the molar mass divided by the mass. So this is going to be 162.2 divided by 90, which is going to give me 162.2 divided by 90 is going to give me 1.8. So I've got 1.8 moles of the iron chloride. All right, let's do the same thing now for the other compound. So hydrogen sulfide. This is probably why my screen does funny things, because I touch things when I shouldn't. Okay, so hydrogen sulfide, what do we know about that? We know that we've got 52 grams. Oh my gosh, stop it, pen. 52 grams of hydrogen sulfide. The molar mass of hydrogen sulfide, so just quickly, sulfide weighs 32.07 and hydrogen weighs 1.01, and I've got 2 of those. So I have 34.09 grams per mole. All right, let's substitute that into our equation. So N is going to be equal to 34.09 divided by 52. Just going to chuck that into my calculator. And that is going to be 0.655. All right, so normally what we would do, so we would have 2 of the iron chloride compounds reacting with 3 of the hydrogen sulfides, right? So they would react in the ratio 2 to 3. But what we can actually see here is we can actually see we've got a ratio of 1.8 to 0.655. So this is about on par. This is pretty close. It's not exactly the same, right? But it's probably, times about 0.9. Now on this side here, we can see that this is a lot less than that. So this is clearly going to be our limiting reagent, okay? So what that means is out of this, only 0.655 moles of hydrogen 2 sulfide is going to react. So now what we're going to do, because it's limited by this reaction, we're going to use this information to calculate the mass of iron sulfide produced in the reaction. So let's do the same thing as what we did before. So we have iron 3 sulfide, and we know, right, that we've got 0.655 moles of this that's going to react. Now, this would normally react to produce, 3 of these would usually react to produce 1 of these. So we've got a third of the amount of moles. So in order to work out the number of moles that react, all I'm going to do is just divide this number by 3 as well. So we know that the number of moles is going to be 0.2. Okay, we can also use the molar mass of this. Now, the molar mass of iron 2 sulfide, I'm just going to quickly, let me have a look. Iron, where are you? There you are, 55.85, and we've got 2 of those, so 2 lots of 55.85. And we've also got 3 lots of sulfur, so we've got 3 lots of 32.07. So in total, the molar mass of this compound is going to be 207.91 grams per mole. Really struggling with this video, aren't I? Oh my gosh. Okay, so our mass, and I've already rearranged this formula, is going to be our number of moles times by our molar mass. So that's going to be 0.2 times by 207.9. So the mass of this that's been produced is 41.582 grams. So I'm just going to round that to 41.58 grams. And that's it. How long did that take us? Probably a little too long. All right, so let's scroll down now. And let's have a look. So we've got, I have just realized too that I've moved my screen. I'm not doing too crash hot today. My gosh. First thing in the morning filming videos before you've had your coffee, not a good idea. Okay, so if you want to have a go at this question, be my guest, pause the video. I'm going to go through. So rescue workers use self-contained breathing apparatus to remove carbon dioxide and water from their exhaled breath. First, potassium oxide removes water from the exhaled breath using the following reaction. So let's just quickly check that this reaction is balanced. I've got 2 potassiums, 1 on each side. I've got 3 oxygens on each side, and I've only got 1 hydrogen. Okay. I think we need to go ahead and we need to balance this reaction first, and then the potassium hydroxide produced is then available to react with the carbon dioxide. Deduce how much potassium oxide is needed to produce 235 grams of oxygen, and then if 123 grams of KO2 is available, calculate the mass of carbon dioxide. All right, so I'm going to pause the video here for a second, and I'm going to come back and I'm going to have both of those equations balanced on the screen for you. All right, this one was a little bit of a crazy one to balance, as you can kind of see, but I've just gone through until I've been able to get to that point. And then I had a look at the second equation, and the second equation, thankfully, is already balanced. All right, so let's go in. So deduce how much potassium oxide is needed to produce 235 grams of oxygen. So in other words, determine how much of this compound here is required to produce 235 grams of this compound here. So I'm just going to clear all this section off just so I have some working space. Alrighty, so the other thing I've just gone and done is I've just worked out the molar mass for each of the compounds that we're interested in, and I've written down the other piece of information that we know, which is the mass. Now what we want to do is we want to find the number of moles. So we're going to use that same formula that we did before. So this is just one that I've rearranged. So if you want to just use the original formula and then just substitute values and rearrange after that, that's fine. Mathematically speaking, we are doing the same thing. So let's go ahead and substitute that into that formula. So the mass is 235 grams divided by 32 grams per mole. And that is going to give me 7.343. So let's just round that to, 7.34 moles of oxygen gas that's going to be reacting. Okay, so in our original expression, so we've got this ratio, and let's write this ratio, 4 to 2 to 3 to 4. And in particular, we've got this oxygen here, which we know we have 7.34 moles of. So what have I multiplied this by to get to here? Because whatever I've done to this, I'm going to need to do the same thing to this expression here. So what I'm going to do is I'm first going to divide by 3, and then I'm going to times by 734, because effectively if I divide by 3, that gets me down to 1 mole, and then if I multiply by 7.34, that's going to get me up to 7.34. So I'm going to do the same thing with this. So I'm going to do 4 divided by 3 times by the number of moles, and that's going to give me 9.79. Yeah, so that's rounded correctly. So I now know that I have 9.79 moles of the potassium oxide. So lastly, what I'm going to do is I'm going to use my mass formula. So that's just going to be the number of moles times by the molar mass. Again, if you just want to substitute that back into the original equation, then rearrange, you can do it that way. I just prefer to have it ready from the get-go. So that's going to be 71.1 multiplied by 9.79. So that's going to give me 696 grams, yes, that's rounded correctly, of the potassium oxide. So let's just quickly check, does that seem reasonable? Well, keeping in mind that we've got slightly more moles and we've got a slightly heavier molar mass of the potassium oxide, then this means that this value here should be higher than our mass of our oxygen. We had 235 grams of oxygen, we've got 696 grams of potassium oxide. Yes, that does seem reasonable to me that this would be a higher mass than what this one would be. Okay, last one. So if 123 grams of potassium oxide is available in the breathing apparatus, calculate what mass of carbon dioxide can be removed from the exhaled air. So again, I'm just going to go through and clear this, and then I will work through part B. So I've gone ahead and I've also written down the pieces of information we know. So we know the mass of this potassium oxide, and we also know the molar mass. So this is just the same value as before. And we've got the molar mass of carbon dioxide. All right, so let's use our formula. So the number of moles is going to be equal to the mass divided by the molar mass. So we're going to have 123 divided by 71.1. And that's going to give me 1.729. So I'm just going to round that to 1.73 moles of this particular substance. Okay, now something to note with this, I've got 4 moles of this that's reacting to then produce 4 moles of this. So it's a 4-to-4 ratio or a 1-to-1 ratio. Then with this secondary reaction with carbon dioxide, this is all in a 1-to-1 ratio as well. So effectively, if I have 4 moles of this, it's going to produce 4 moles of this, and therefore it's going to be able to remove 4 moles of carbon dioxide. So I know that the number of moles of carbon dioxide then is going to be the same as the number of moles of the potassium oxide. So that's going to be 1.73 moles. So that's good. That makes our calculations nice and easy now, because we need to work out the mass. So we're going to use that formula that we've rearranged, and that's going to give us 44.01 times by 1.73. So we're going to have 76, what does that round to? 76.14 grams of carbon dioxide that's been removed from the exhaled air. Okay, I think that was all of the questions. Oh, there is one last one. Let's hope we have enough time. We've got 3 minutes. Okay, so chemical equation for photosynthesis is 6 CO2 plus 6 H2O, which forms glucose and 6 oxygen. So synthesize the concepts covered in this chapter to explain why plants in deserts fail to produce enough glucose to grow. I don't think we actually even need to do any working out or anything for this. I think this is a pretty simple concept. If this is a limiting reagent, right, if I don't have this particular reactant, how the hell am I going to produce this particular product? Okay, so that's why plants in deserts are pretty slow growing, because they do not have enough of this to produce the reaction. All right, done. That was quite a complicated video. I'm sorry for all of the little stuff ups and the having to stop and start and everything like that. Hopefully that you're actually able to get something out of this, and I'm going to go have a coffee and get my brain back switched on. All right, talk to you soon, guys. Bye.